Okay, my name is Sharkov. Some of you might probably already know me from my previous talk at Go Meetup here in Zurich about the optimizing the hell out of a GraphQL Lexer. And I'm working as a backend engineer at iterator. Some of you might know Ricardo, Anibis, MotoScout, AutoScout, HomeGate. That is all part of SMG. And here I am at iterator. So advertisement over. Actually, I didn't like the first cover picture much because it makes me look like I'm some pesky designer or something. So that's better, right? That's JSON. We're all familiar with that. But there are things that aren't right about this JSON. Can you spot them?
Windows.
Yes?
Missing backslashes and pieces were done?
Yes, they are unescaped. That's correct.
There was a comma mistake after your Russian name over there.
No, it's fine. That would actually be correct.
Really?
Yes?
Keys cannot be duplicated, and the comma at the end can.
False. The specification doesn't define keys. So it's up to the implementation to handle this case. Some might just use the previous values. Some might throw an error. It depends on the implementation. The spec is.
So it's your logic.
Yes, sure.
Approximate atoms in body probably overflows an integer at least.
Also not defined by the specification. The specification only defines the syntax of the number, but it doesn't specify the range. It's up to the implementation.
Comma missing a single line.
Where?
Comma.
Where?
Last name.
Oh, there's a trailing comma, yes. There's a comma.
There's a trailing comma, exactly.
Oh.
And then trailing commas are not allowed by the specification. So anything else? There's still one left.
007.
Exactly. The number here, 007, is actually incorrect. And still one more left. Can you spot it?
The emoji was
The zero byte has to be escaped correctly, and the escape sequences need to be 4 hex digits. So as you can see, parsing JSON is a minefield. And I had to find it out the hard way. And there's actually a great article about this, so please make sure to check it out if you ever happen to be working with writing a parser. But why are we actually talking about JSON parsing right now? Well, you see, before I started at Tutti, I was working on a startup project we called GraphGuard, and a small team of 3 people, essentially, for half a year. Spoiler alert, it failed. But it served as a great field for experimentation and learning, and the experience that I gathered, or parts of the experience that we gathered, I want to share with you today. Probably most of you are familiar with GraphQL by now. Raise your hands if you've already used it in production. Raise your hands if you just used it. Okay, I see quite a few people. That's good. So, as you might probably know, GraphQL is a language that allows you to define a schema on the server, which the client can then grab data from as they wish, according to the schema. And while we were working on GraphGuard, the startup, we were developing a proxy server that would sit between the internet and your GraphQL server. So essentially, it would receive requests, do some black magic, return a response from the GraphQL server. But when you're developing a proxy server as a business product, then performance becomes a business value. Because let's admit it, nobody likes slow software, especially when they have to run it on their own infrastructure. So the more throughput there is, the more money we can save, the less servers we need, and the less engineers we need to maintain those servers. The lower the latencies are, the better UX we can actually provide to our end users. And the better resource usage is in general means we can not only save the money, but we can also save our planet and environment. But let's not call it premature optimization, because that sounds terrible. Let's call it performance-oriented programming. And that term I first confronted at Casey Muratori's courses. And if you're really into that, if you're really into code optimization and stuff, I really recommend his course. Essentially, it's about being aware of the hardware that your code is going to run on, and about making decisions that allow the compiler to generate better code that would then also allow you to reuse memory, for example. And memory is actually a hell of a problem, because dynamic memory allocations are the low-hanging fruit when it comes to code optimization. So we defined for ourselves a rule that we would never dynamically allocate memory at runtime. So from the start, when we start handling a request to the end where we return the response, we had no allocations. That allows us to have a consistent latency, don't have inconsistent garbage collections here and there, and so on. So we would just allocate memory, set sane limits to our software, allocate memory at initialization time, and then reuse it as much as possible. That, though, is difficult to do when third-party code is involved. And as you might probably know, GraphQL allows you to use variables which you then provide the values for in JSON. So on the left, you have title, description, assignee, scope, and then on the right, you have the JSON that fills in those values. And while we were working on implementing this to our engine, we faced the problem that our engine wasn't able to work with JSON directly without having some kind of intermediate engine internal code. So we had to translate it. And, well, while working on this sub-project, I realized that a lot of my time was going into the topic of JSON parsing, and a lot of my free time as well. And eventually, I tested out very different implementations, different libraries. One of the oldest one, for example, is GJSON. You probably already know it. And on the bottom there, you will see a new kit on the blog, which is licensed under the BSD3 license. But if you have any problem with that, just talk to me. We might change it. That's up for debate. But I think it's still a great license. And it's very popular as far as you can see. And yeah, I spent like a year developing that in general. But when I started working on GraphGuard, I just took the work that I already did like a long time before, and I just polished it up to become a finished product. And what is JScan? It's essentially a JSON iterator, and likely, maybe the most efficient one. I learned to be very gentle about claiming this kind of stuff. It's very, very dangerous to make such claims. But anyway, it's pure Go. There is no CGO, no platform-specific assembler whatsoever, just pure Go. And it's fully compliant with the JSON specification, RFC 8259. What it's not is, it's not a marshaller and unmarshaller. There is enough of this stuff around. I don't need to reinvent the wheel. So there is no such functionality in the library, and I finished on other aspects, as you will see. But I forgot to mention that you can actually use JScan to build your own task-specific JSON parsers if you need the efficiency. So let's just imagine a very imaginary case where you have this GraphQL variable traverser interface, and it only has one method, traverse JSON. This method calls onVariable for every variable in the object, which is like the first key in the JSON object that you get. That is how GraphQL handles variables. And then you pass in the name of the variable and the value type. It's just an enum, essentially. First, and like in any situation, we always use the standard library. That's the correct approach. And that's very easy. Like we can just unmarshal our input into a map of string to any, then loop over the key value pairs, use a type switch to determine the type of the value, and we're done. Very easy. There's just one problem. It's very inefficient. There are 77 allocations each time we do this operation. And it takes 45 microseconds, which doesn't sound like a lot, but you will see that it is. And by the way, we were parsing this JSON here, where I conveniently replaced long strings with the rock emoji. We can actually do better. What we can do instead is we can use JSON raw message to avoid having to parse or like allocate objects for the values themselves, because we don't care about the values, we only care about their type. So what we can do is we can have a mapping which maps certain characters to their respective type identifier, and then we can just essentially unmarshal into this map and then go for each and then take the mapping essentially. And this is much better. It's 36, just 36 allocations, but it's still 33 microseconds, not the best. Not great, not terrible. So what I've done for this talk specifically is I've written implementations for this interface in different libraries and compared them for you. I was trying to make sure that I did it correctly. There may be mistakes. So you're invited to check them and point out if there were any. But I did my best, and what I found is we have this byte-dense Sonic library, which utilizes SIMD instructions, single instruction, multiple data, but it only works on AMD64. It doesn't work on ARM. And on ARM, as you can see, it's actually one of the worst. So not a great trade-off, to be honest. And we still have 12 allocations. What's next? We have GJSON. GJSON is pretty good at both ARM and AMD64, but it still allocates memory. We still have those 3 allocations, and it's still 32 microseconds. It's fine. You can already see that we can do better, right? So there is this library called JSON. It is a very popular parsing library for JSON, like 12,000 stars, or what was it? And it's doing well. We're coming close to 0 allocations, but it's still not ideal. And then there's this relatively new library called GoFasterGX, and we're finally there. No allocations whatsoever. And as you can see, once you start having no allocations, the cost of executing goes down drastically. We are 1.6 microseconds here. It's like almost like 30, 40 times faster than the standard library. But we can actually do a little better. And I managed to squeeze a tiny little bit of performance out. And you will see that later that it's not actually noise. But what the hell is this? Like, fast JSON? What? 720 nanoseconds? 12. It's like, this is insane. How did you do that? And fortunately, everything is open source. So I studied most of the implementations, most of the algorithms to learn their tricks. And I've learned the trick of FastJSON. FastJSON utilizes the package bytealk. It's hidden in the internal packages of the standard library, and it provides hand-optimized assembler code for these specific functions, index byte and index byte string. What it does is it returns you this, the index in the string or slice of this particular byte. And FastJSON makes heavy use of that. Their whole algorithm of parsing depends on this stuff. And this is what makes it fast. But there's a catch. If you put a null character in the string value and then pass it to the validator of FastJSON, it will actually return the correct result. It will tell you that strings cannot contain control characters. That is correct. But once you start parsing, it doesn't care anymore. Well, There's a problem. It's actually violating the specification. And let me read it to you. A representation of strings is similar to conventions used in the C family of programming languages. The string begins and ends with quotation marks. All Unicode characters may be placed within the quotation marks, except for the characters that must be escaped. And those are the quotation mark, reverse solidus, and the control characters. So fast.json is essentially violating the specification to be faster. Well, turns out it's actually a known problem. The author is not going to do anything about it because, well, he sacrificed spec compliance for performance. I mean, it's a trade-off you can take, but I unfortunately have to disqualify because a JSON parser needs to be JSON standard compliant. So yeah, we won! And again, is this really a difference, or is this just benchmarking noise? Because when you test, your CPU might be in different shapes. Sometimes it's drunk, sometimes it's not. And well, I've tested the hell out of it. I've spent months writing benchmarks, executing them, and it takes a lot of time to just execute it for two platforms, for ARM and AMD 64. And for M1, it's terrible. You cannot even instruct the CPU to just keep a certain frequency, which you can do with an AMD CPU, for example. So it's difficult. But I've composed, as much as I could, benchmarks for you. And here in this benchmark, we're processing a 26 megabyte JSON file. And you can see that JScan is being about 38% faster than Go Faster, the fastest out of the competition here, and 46% faster on the M1. There is this weird NASA JSON file that I found, was also used by the different other benchmarks, and it's about 125 kilobytes. As you can see, we're still faster, 21%, 33 on ARM. There is the small JSON file. It's just 336 bytes. And as you can probably tell, our difference is already going down. So we're just 14% faster on AMD 64. And of course, it's not always rosy and cozy, because once we start approaching this very tiny JSON file, which only has one object and one key, well, we're 75% slower. But how big of a difference is that? 3 nanoseconds. I mean, at that point, I didn't care anymore. So I decided not to invest any more of my time to try to beat this benchmark. But there is one case I cared about a lot, and that is malicious JSON. When someone crafts malicious JSON to take advantage of vulnerabilities in your JSON parser. And one such vulnerability can be very, very deeply nested objects. You can and you should set limits to how deeply nested your JSON input should be. But I have taken 1024 of these characters and added an EOF at the end. And as you can probably tell, we must grow a deep call stack when we're trying to parse an array. And once we encounter that error, we have to go all the way back. We have to return from every function. And that's called stack unwinding, call stack unwinding. That's not free. And when you do that, don't do that in your JSON parsing library. You can do that in your microservice business code. It's fine. But don't do that in the JSON parsing library. And you will see that actually some people do. Yeah. Look at this number here. It's 10 milliseconds. It's 4,100 allocations due to these error allocations that fast.json, ironically fast.json, required for 1,024 bytes. This is terrible. And I have optimized the parser in order to avoid this situation and was able to beat this benchmark by a hair strain, and that could already be some benchmarking noise. Let's ask the questions at the very end, and if we don't have any time, like after the talk, but still have something to show you, a movie. I've directed it. It's starring State Machini, string parser, Skipper Spacey. These are the main characters. So let's start with the main role, State Machini. He's mad, can be described as insane. Nobody likes him really. But he still manages to get casted to roles nobody else can play. Because he brings 17 labels and 95 go-to statements to reduce the overall count of functions that we're calling in the JSON parser to just one. And we have no nested calls whatsoever, which allows us to return from the function whenever we want. And it is not going to cost us anything, which is great to fight the situation that we discussed before. And the other small inline, functions are inlined anyway. This is some snippets from the code. And let me quickly explain to you. Like when we're approaching a value up there, there's a label. We're going into a switch statement, a conditional statement. And then let's say we face an opening bracket, an opening curly brace. Then we go to the value object label, which here, you probably should see, yes, exactly. Which here then checks for UF, end of file, then skips over spaces if necessary, checks whether the object closed, and then goes to after value, or manages locally a manually managed stack, and then goes to parsing an object key. It's complicated, it's spaghetti. You shouldn't do that in most of your code, but this helps making it real fast. And you will also see other examples of this. Next character, Skipper Spacey. He is a small but very important unique character because he is the only function in the movie, or in the state machine. He skips over irrelevant bits of JSON like white spaces, tabs, line breaks, and carriage returns. And if you would imagine his code, you'd probably think about something like that. Like a for loop, which inside switches on the character that we're currently at, and then determines, is this a space or not? If it's not a space, okay, we can subslice and return. And you would probably ask yourself, like, okay, for 130 spaces, for skipping 130 spaces, it takes 50 nanoseconds. That's nothing, right? For no spaces, 1.7, one space, 2.8 nanoseconds. This is absolutely nothing. We don't care about these numbers. And we cannot make it any faster, can we? Like, the compiler should make it faster. Not exactly correct. The compiler, we can actually aid the compiler to generate better code to make it even faster. And as you can probably tell, we can go from 50 nanoseconds to just 30 nanoseconds by changing the code a little and applying several tricks here. First of all, loop unrolling. Some of you might have already heard about this optimization technique. It essentially takes 8 pieces, 8 characters, and tries to do them in one go. And then it returns to the loop management code. So it doesn't have the loop management code for every single character. Instead, it does 8 as long as it can. And there's a second trick, a lookup table. Remember the lookup table from before? We're actually taking the value of the character, like the ASCII number, and we're using that as an index in an array of 256 bytes. And then we can classify, based on the number that we get from the array, whether it is a string we care about or not. So eventually, when a modern CPU with its branch prediction capabilities sees that code and goes over that code, it can just skip through those ifs as if they weren't even there, because it manages to correctly predict where to go next. And this code helps it do that. And as you can see, we don't pay anything extra for no space, but we actually gain performance, and this quickly adds up. And last but not least, string parser. She's the actual MVP of the movie because JSON is mostly strings, and her role shouldn't be, therefore, underestimated. Her performance determines the performance of the movie. And again, this is a naive implementation of it. We have a loop, we have a switch, and then we are acting differently based on the characters that we see. Again, we can do a lot better by, again, utilizing lookup tables and unrolling the loop. And in this case, if you can tell, as you can tell, in the Wikipedia regex data set, we were able to go from 94 microseconds for a very long string to 30 microseconds. That's 3 times as fast with just pure Go code. And that is the lookup table. Don't even look at it. It's cryptic. You won't get it right now. You can take a look at the source code, and then everything will start to make sense. But as I explained, this is the key part here. It's 256 bytes long, and every byte in it is a classification integer, essentially. What's the roadmap for this project? Well, actually, I prefer correctness and stability and performance over features. Therefore, there isn't going to be much features here, but I consider adding support for I/O reader to be able to read files that are bigger than memory. For example, if you have to statistically analyze some very huge JSON file, you cannot load it into memory. And that is where this feature could be useful. And a tokenization API besides the iterator could probably be nice. But yeah, where we are going, there's no roadmap necessary. And everything is open source. I invite you to take a look at it and probably try it and prove me wrong, because this is very crucial. I have made very important statements, and those can be proved wrong very quickly, and you could be one of the one proving me wrong. That's it. That's the last slide. I would thank you for listening, and if you have any questions, I guess we have no time left. Just ask me later after the presentation. Thank you very much.